pop quiz. Yeah, it's that time. Okay, so what is the pop quiz here? You're looking at my screen, and what you can see is there's a parabola. The parabola you can see is this one up here. It's the one in red, x squared plus 3x minus 4. So the pop quiz is to tell me for what values of x is this parabola less than 0. And if you have the graph in front of you, it's pretty easy. Take a second, think about it, but it shouldn't take you very long, because you can actually look at this and you can say, well, there's the roots. And when is the parabola less than 0? For all these x values that create the parabola to go below the x-axis. So the x values would be x is bigger than -4 and less than 1. So all the x values along here, and if you wanted to actually write that out, it would look like this. Now don't worry about that part because Desmos has a funny time with inequalities, but your solutions would look like this. Okay, that's how we could answer the question, when is x squared plus 3x minus 4 less than 0? We'd say x is greater than -4 but less than 1. So that should be pretty easy if you have the graph. But now here's the thing to think about. What if you don't have the graph? What if I make that disappear and now you're answering the same question except you cannot see the graph? So maybe this is a textbook question and you just see the algebra rather than a graph. What we're going to do today is we're going to look at how you can actually figure this out. Now, if you're thinking, and you don't even have to think that hard about it because it's almost obvious, the obvious answer would be, well, if I had the graph, this would be easy. So what do? Graph it. You don't always want to graph everything, though, and sometimes you don't have your graph paper handy. So what you can do is you can use a little bit of algebra. Now, unfortunately, if I just did this, and I said solve that, first of all, Desmos can't really do it. If I click on it, it's going to be weird. Second of all, you can't just get an answer, because what's going to happen when you try and solve this is this stuff on the left maybe will get factored, but then you're going to have two factors multiplied by each other, which is less than 0. And that doesn't even make a whole heck of a lot of sense, because you've got to get it down to one value of x. Now, if you're not totally sure what we're talking about, well, stay tuned, because we're going to look at this and see how we can solve it. In case you're curious what does happen if I show the graph here, we get a band like that. What Desmos is actually showing is it's showing the x values that would solve it, but it's also giving us this weird up and down space, so it's not very good. Just because people might be totally curious, this is what the graph looks like. The answer would be x is greater than -1, and it would be x is less than, that looks like about 2/3. But without this graph, how can we do it? That's what we're going to find out. So, our last section, section 4.9, solving inequalities algebraically. Let's have a look. Okay, so solving linear inequalities using algebra. This is actually pretty easy, so we'll just go through this pretty quick. When it's linear, no big thing. So when we're solving linear inequalities, all you have to do is isolate x, as if you're solving an equation. So the only thing you have to remember here is inequalities are treated like equal signs. There's one small rule or exception. They get flipped when you multiply or divide both sides by -1. We've talked about this before. So let's just do one example, and we're not going to spend a ton of time on this because, like I said, it's pretty simple. So if we have this situation, this is less than this, so 3x plus 5 is less than 15 minus 2x. You just got to isolate x by itself. So there is one thing here. I'd like to try isolating x on the left and then isolating it on the right just to illustrate a point. But so we'll do this two different ways. Okay, so one way you can do this is to go 3x plus 5 is less than 15 minus 2x, and then you want to get x on the left, so we're going to add 2x to both sides. We're also going to subtract 5 from both sides. So we'll have 5x on the left is less than 10, and then isolate again. X is less than 2, and that would be our answer. Simple. Because we never divided by negative on both sides or multiplied by a negative, don't have to flip the inequality. If we chose to do it this way, we would subtract 3x, because if we're trying to get it on the right side, we'd have negative 5x here. We'd actually subtract 15 over here. And we would have 5 minus 15 would be negative 10. So what we would do at this point, we would now divide both sides by negative 5 to isolate x. And this is the key thing, because right here, so you're dividing by negative. So what's going to happen is this is still going to be x. Negative 10 over negative 5 is positive 2. But because we did that divide both sides by negative, we're going to flip the inequality. So that one gets flipped. So let's just make a little note there. Okay, so the answer is going to look like 2 is greater than x. So you notice if we didn't flip it, we'd have 2 is less than x, whereas on the other side we had x is less than 2. Those are obviously not the same. These two statements, though, these are the same statements, right? Saying 2 is bigger than x or x is less than 2 are the same. Anyway, you can solve one way or the other way. These are two different methods, but for the general, overall kind of idea, it's pretty simple. Keep that inequality where it is, and you can just flip it once in a while. The majority of what we're going to do today is on quadratic inequalities, and this is where it gets a little bit trickier. So if I simply did something like what we had in the beginning, I'm just going to write a couple things down here. This would be, I guess, what, 3x, this would be a plus, this would be a minus, and let's say I wanted to figure out when this is less than or equal to 0. You can't just isolate x, right? That's the whole deal with these quadratics. What you can do is you can factor, and you can have this kind of business here. But here's the problem. If you just simply say, well, x is equal to negative 4 and x is equal to 1, what does that have to do with less than 0? We're trying to find values of x that make this entire side less than 0. And if you think about it even harder, it's going to get even trickier, because we can easily find values of x that will make it 0, but what values of x would make this less than 0? You have a lot of options, because if this is negative and this was positive, then the whole thing, when you multiply negative positive, you're going to have a negative. Negatives are less than 0, that's great. But what values of x can make this negative? And those values of x have to also make this positive, because if you found some value of x that made them both negative, you'd have a positive and it would work out. And if it gets kind of weird and confusing, that's because although the concept should not be too hard when we're looking at it here. So let's just take a second, just remember that what we're going to do when we're solving quadratic inequalities and you're not graphing, you generally can't isolate x. That's kind of the whole thing. So everything I was just saying, it's all about that. You can't isolate x, but you can find critical points. And remember, critical points, these are x-intercepts. So what do? We always want to move all terms to one side to make the other side 0. So if you had something like this, x squared plus 3x was less than 4, we don't like that. You'd always want to make it x squared plus 3x minus 4 is less than 0. Always get 0 on one side. That's kind of the whole deal. You're always going to replace the inequality with an equal sign, because we're always going to solve an inequality by first figuring out where it's equal to 0, and then we'll deal with the idea of when it's less than or greater than 0. And then we'll solve for the roots, which are the critical points. And that's something we did. This is all chapter 3 stuff, so this should be pretty easy at this point, right? So this is all chapter 3 business. Now, one thing we have to keep in mind here is the critical points. The whole reason why we're doing this is it gives the ends of the intervals. So if we have a graph, and let's say we have a parabola, and this is something, but I don't really know how to solve an inequality, but we can always easily solve for the equal 0 points. So here and here, those would be the critical points. Now, if we're looking for when it's greater than 0 or less than 0, it doesn't really matter. But what we're going to do is we're going to say that there's an interval like here where we can see the parabola is bigger than 0. Over here, the parabola is also bigger than 0. And in between, the parabola is less than 0. So if I was looking for when my parabola would be, let's say when y is less than 0, then what I would do is I would say, okay, well, if we know the critical points, those are like the cutoffs where the parabola switches from being positive to negative. And then I know those are the endpoints of my intervals. The only thing I can't figure out right away is whether everything to the left of the critical point is a solution or everything to the right of the critical point is a solution. Same thing with the other one. So the way we're going to have to figure this one out is we're going to have to use something called a test point. So when we get these intervals, like if I did this on a number line, we'd have our critical points here and here. My critical points. And what I need to do is I need to pick some value in an interval. This is an interval. So is this one. So is this one. So if I want to figure out whether a certain interval satisfies the inequality, from here on out I might call it a winner or a loser, I need to use some point in the interval. So I'm just going to pick a random point. So let's say the critical points were, what do we have in the last example, like 4 and 1. I pick some point over here, maybe like -5. And if I put that into my equation, or inequality I should say, and it satisfies it, then I know this is a winner. If it doesn't satisfy it, then I know it's a loser. And if one point in the interval is a winner, then they're all winners. Yay! And if one point is a loser, then they're all losers. If -5 doesn't work, then -6 or -7 or -8 won't work. So that's the idea. We'll see how this works by doing an example. Okay, so solve the following inequalities by algebra. So we're not going to graph this, but we're still going to solve it. And we can check later maybe if we want, but for now let's just do algebra. So the first thing we're going to do is we're going to make this look like an actual quadratic. So it's nice when it's equal to 0 on the right side. So this is just rearranging it. Now I want to find the critical point. So finding the critical points is as simple as saying, let's set this bad boy so that it's equal to 0. This is how we solve for x-intercepts, which are critical points. So this one we can do, I believe this is factorable. Maybe I won't be a hero and skip too many steps, but let's see. So I'm just going to use the AC method. AC, 2 times 3 is 6. So my numbers have to be -6 and -1. Okay, so this will be 2x squared minus 6x minus x plus 3, 0. And that's 2x, x minus 3. Take out a 1 there, x minus 3. Okay, so the way I factor this, decomposition, still my friend. Okay, so what we found is x is equal to 1/2 and x is equal to 3. I just figured out that when I have a parabola, 2x squared minus 7x plus 3, it's equal to 0 at those 2 points. So those are the x-intercepts. So we're going to go one step further here. Now we're going to answer the question, when is it greater than 0? So there's kind of 2 ways of doing this. The main way is using test points, but another way is even kind of thinking about it as a graph. So you're kind of doing a little bit of everything. Test points, algebra, graphing. So the way you do it with test points is we're going to do it very mathematical and rigorous, but there aren't always shortcuts. So here's 0. Let's say 1 is here. So I guess one of my critical points would be at a half. And it'll go negative, negative. We'll try and space this out appropriately here. I guess I don't need much in the negatives, but I do need to go all the way up to 3. Okay. So there's my other critical point. So this thing I'm sort of mumbling about graphing is the idea that this is a 2-dimensional thing, but I could easily draw the, sorry, I said 2-dimensional, I meant this is a 1-dimensional thing. I could easily make it 2-dimensional. Here's the x-axis, here's the y-axis. When we draw a number line, we have to understand we're just drawing the x-axis, we're never drawing the y-axis, but it still makes sense to think about. So you could argue that this is an upward-facing parabola, and if I want to know when is it greater than 0, then what I would do is I would say, well, I know it goes to these 2 points, it's upward facing, so it's got to be doing this sort of business. And when is it bigger than 0? Now I can see that this part here and this part here are the parts bigger than 0, and that corresponds with values of x to the left of 1/2 and to the right of 3. And most of you are going to find that's the easiest way of doing this. So why am I even bothering with this idea of test points here? Because test points are actually going to be useful in a lot of other applications, and they're a good second way to check things. So I'm just going to erase all this here because I would really like to illustrate the use of these test points. So what a test point is it's this idea that we can think of this in terms of 3 different intervals. So this is interval 1, and I'm going to even give it the Roman numeral I. This is interval 2, and then everything over here is interval 3. So everything to the right of 3. So if we want to test intervals with a test point, so we're going to test interval 1, and we're going to use any value of x, like literally any value of x in that interval to see if it satisfies the equality. So any value of x you want, I'm going to pick, let's pick 0. Because when you're picking any value, you might as well pick the easiest one. So I'm going to use this one right here. That's my test point. I could have used -1 or -2 or whatever, but I didn't want to. Let's test this guy. So we're going to test 0. That's going to be the point that I use in interval 1. And while I'm at it, let's grab some other points from the other intervals too. So in interval 2, let's see, what's a point in there? I'm going to use this guy here. That's a good test point. 1. Picking simple numbers. I need something to the right of 3. So you know what? Let's go with 4. That will be my other test point over here. Okay, so if I'm testing interval 1 to see if these solutions satisfy the inequality, I'm going to use x is equal to 0. Again, any point works. So what I'm going to do is I'm going to put this back into, I'm going to use this in, and you can either use the original or the simplified version. It's actually safest to use it in the original. So I'm going to go like this. I'm just going to double check to see if that is true. So this would be 2 times 0 squared minus 7 times 0. Oops, we don't have an equal sign there. So is it true? Is this a true statement that 2 times 0 squared minus 7 times 0, is that greater than -3? Well, that's like saying 0 is greater than -3. Yes, it is. So what that has done is that has told me that 0 is a value of x that satisfies this equation. And because I know the critical points are at 1/2 and 3, I know that every point until you cross over a critical point, any point in the interval will also be a solution. So because that's a winner, I can therefore conclude that everything to the left of a half is also a winner. Therefore, all points in interval 1 are solutions. I don't have to write this every time, but I'm just being explicit here. Therefore, what can we say? X is everything less than 1/2. Now, it's not enough to just test interval 1, because you've got to test 2 and 3. So let's actually test interval 2. So I'm going to use, I suggested using x is equal to 1. So a little quicker here, we'll just go through 2 times 1 squared minus 7 times 1. Is that greater than -3? So what's that? 2 minus 7, that's -5. Is it true that -5 is greater than -3? No. Therefore, maybe I shouldn't use an x because I'm using x's everywhere, but this is not true. Okay, so what can we say here? No points in interval 2 are solutions, which is what we might have guessed before, given the shape of our parabola. I'm going to test interval 3, and I'm not going to say too much here because it's the same process. That's what, 32 minus 28. That's supposed to be a negative sign there. Is it true that 4 is greater than -3? Yep, you bet. Therefore, we can also conclude that x is greater than 3. Okay, so that's the way you would write it, actually. So you'd write 2 separate statements, x is less than 1/2, x is greater than 3. Pretty much it. Okay, this one I'll go a little bit quicker. In fact, I'm thinking I'll go a lot bit quicker because it's a similar sort of thing. So solving this guy will be 5x, blah, 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 blah. Okay, so we're going to move everything over to one side. I'm going to take 5x and move it over here. Okay, so now we set this equal to 0 and we get our critical points. So this looks like it's probably factorable. That's going to be, I'm just going to skip a couple things. I can kind of see here it's going to be like this. I'm doing AC in my head. This is not a lesson on factoring, so don't feel too bad, which is kind of jumping ahead a little bit. Okay, so 2x plus 3 and x minus 4. So this tells me the critical points are, therefore, the critical points, x is equal to, that's going to be, let's see, negative 3 over 2, and the other one will be x is positive 4. So what this will look like on a number line, there's 0, here's 4, here's negative 3 over 2. Okay, so if I'm using test points, I got to pick test points from each interval. In fact, maybe I won't even draw this one because I really want to just make it clear. There's only 2 critical points in the right here and right here. Okay, I do have like 0, 1, 2, 3, all that sort of stuff. I guess negative 1 would be there. Okay, now we just have to think in terms of critical points, in terms of intervals. What do I want to test? What do I want to do? So if you haven't done this at all, pause the video, think about it. Can you finish it from here? So these are the intervals. And we should really test each interval. Now some of you are probably going, well, hold on a second. If this is a parabola and I know it opens up and it just kind of goes like that, do I really need to test all 3 intervals? Doesn't it like go winner, loser, winner, or loser, winner, loser? Like, doesn't it just alternate all the time? And the answer to that is it actually does a lot of the time. And if you're a clever kitten, you can probably determine that it actually does. I can't give you a percent, but most of the time. There are sometimes exceptions, and I think some of the next examples will have them. Let's go through this. I'm going to test. Something from interval 1. So I'm going to test interval 1. I'm going to use x is equal to negative 2. Is it true that 5 times negative 2 is greater than or equal to this? Now I don't know why I put an x squared there. Okay, is this true? So that's negative 10, and that is greater than or equal to, let's see, that's 2 times 4 minus 6. That's 2 times negative 2. So is negative 10 greater than or equal to, is that negative 4? And it turns out that is absolutely not the case. So let's test interval 2. So let's pick some point in interval 2. Again, I'm going to go with x is equal to 0 because that's real easy. It makes the math super easy. Is this true? This is 0. And this is 2 times negative 6. Is this true? 0 is greater than or equal to, yep. Yes, that's a winner. Same thing with test 3. Let's pick a point over here. I'm going to test 5. I'm going to use x is equal to 5. Okay, so is it true that 5 times 5 is greater than or equal to this? So let's see, that's 25. 25 minus 6 is 19. What's 2 times 19? 38. Is that true? No, that's not true. Okay, so what I see here is I see interval 1 is not full of solutions. Interval 2 is full of solutions, and interval 3 is not full of solutions. So how do I express this answer? This one is nice because we can actually write this as one thing. You don't want to say like x is greater than or equal to negative 3 over 2 and x is less than or equal to 4. No, let's just combine it all together. X is simultaneously bigger than or equal to 3 over 2 and less than or equal to 4. Why is this less than or equal to instead of less than's? It's very simple. It just has to do with the fact that we had an equal sign there. Okay, so that's how you express the answer for that. There's 2 more. These, let's see if these have any twist to them. Let's go ahead and try this one. Or you should probably try this first. It's always fair to divide both sides by 2 if you want. Now, if you're looking at this going, that's different. Well, yeah, I can see why this example's here. Okay. So we have a situation where here's our parabola. It's a perfect square trinomial, and we can figure out the critical points. You don't even necessarily have to show all the time, right, this step here, because, well, okay, we'll just do it. X is equal to 3. Okay, that's the critical point. So what this looks like on a number line is it only has 1 point, 1, 2, 3. Right here, we have 1 critical point. We don't have 2. So in this case, we don't have 3 intervals. We have 2 intervals, everything to the left of 3 and everything to the right of 3. So if we're going to test some points, we're going to test interval 1, and we're going to use x equals, and pick anything left of the number 3. You're thinking 0? Good for you. Okay, so 2 times 0 squared minus 12 times 0 squared, then equal to -18. So is this a true statement? Is 0 greater than -18? Yuppers. So I'm going to put a big fat check mark above there to remind me. And then we're going to test interval 2, and we're going to use any point to the right. So you can pick any point. I'm going to use x is equal to 4. So is this a true statement? That's 2 times 4 squared. So 4 squared is 16, so that's 32. And then, let's think about that. What's minus 48? Is that? Okay, so what's that, -16? -18. Okay, so that's a winner. Okay, okay, there we go. Check, check. So what do we say if both intervals are satisfying? What we can say is therefore x just belongs to all the real numbers. This is basically saying all x is a solution. So if we put any value of x into this, it will satisfy it. Every single value, every single number you can think of will be true in this case. That's pretty nifty, actually. Okay, and then the last one, D. We can go back to red. For D, we have this here. Okay, so is this factorable? So let's just do a little AC thing. AC equals -3, it's 15, or the two numbers, 2 factors of 15 that add up to -6. I'm not seeing them. Now, I'm going to feel pretty dumb because this is on the internet, but I can't think of a way to factor that. So I'm going to see if maybe I need to cheat a little bit. And I'm going to use the quadratic formula. So I'm going to set this equal to 0 because I want to find the critical points. And I'm going to actually use the quadratic formula. So I'm going to go 6 plus or minus. So b plus or minus b squared minus 4ac all over 2a, so that's -6. So what do we got here? So 36 minus 4. Okay, so what's 4 times 3? That's 12. 12 times 5 is 60. 36 minus 60. No. This is 6 plus or minus 36 minus 60. Oh, that's what's going on. Okay, this is a bugger. Okay, there's no x-intercepts, therefore no critical points. So what the heck do I do here? Let me think about the number line. What do I do? So here's 0 and 1 and 2 and 3 and all this sort of stuff. So remember, what this is saying is this parabola never touches the x-axis. So say it with me. If the parabola never touches the x-axis, it never changes sign, which means that it's always positive or it's always negative. Gosh darn it, which is it? And how many intervals are there for me to test? And the answer is, the whole thing, the entire number line. All of this is an interval, one interval. So all we have to do is we just have to test one interval. So literally take any number and test that one number. So we're going to test, give myself very much room, but we're going to test x is equal to 0. If this is a winner, then they're all winners, and if it's a loser, then they're all losers. So if I actually go negative 3 times 0 squared minus 6 times 0 is 5. That is negative 5. Is negative 5 greater than 0? No. So everything's a loser. So what's the answer? No solutions. Or if you want to sound really fancy, x is a 0 with a line through it, which is a way of saying no solutions. Okay, now there's some word problems. We're going to do this in a couple of parts because this is enough knowledge for people for today, I think. But one thing I'll just have you think about here, I'm talking about test points because I'm really emphasizing that idea. You can still use graphs to help you. So if you understand what the graphs of all these look like, you can actually answer this pretty easily. Again, test points are useful, but they're not necessarily the easiest thing, but they will be useful later on in math. So you get an introduction to them. Keep in mind, could we have solved this one just by thinking about the graph? And we absolutely could have. So let me just find my cursor there. This is an upward facing parabola, so we know it's going to do something like this. We know it's going to be winner, loser, winner. We didn't even really need to test point that. We could have just figured it out that way. Same thing with this one. This one's a little trickier, right? So when the graph gets uncomfortable, I like to think about test points. But could we do a graph thing? So here's the equation. Okay, so this is an upward facing graph. And it's got to be, when is it less than 0? So it's still upward facing, so it's still going to do this sort of thing. When is it less than 0? Well, that would be everything in this interval, which makes sense because here we are. It's all less than 0. So that should work. Let's think about the picture for the next two. I did a little rearranging here and I got this. This is an upward facing parabola. But here's something else. We're in general form, so what I can easily do is I could look at this and say this is the y-intercept. Well, if the y-intercept is positive and it's upward facing, that means my parabola is like way up here somewhere. And when is it greater than 0? Well, everywhere, right? That should make some sense. My last one. So this is why we don't have any solutions. This is a downward facing parabola. And it's got a negative y-intercept, which means it's like down here somewhere. When is it greater than 0? Never, because it never crosses. So in addition to the idea of test points, which support your ideas and kind of protect you from making a mistake if you're understanding if the graph is wrong, you should definitely think about the graphs as well, because this can seem pretty intimidating and difficult, but it's really, really, really rooted in some common sense. When is the parabola above or below the x-axis? And if you know what the graph looks like, you can solve it real easy, and you can use test points to help support your understanding of it. Anyway, we'll deal with the remainder in another video. Thanks for watching.